So, good evening. So, we'll start the class.
Good
So,
evening,
for
sir.
the next, good evening. For the next 4 days, we'll be discussing. Today, we'll be discussing the earth processes. That's the block one. Tomorrow, we'll discuss the climatology and meteorology, then hydrology, then natural hazards. These are the four topics, or there are four blocks. Each block consists of 4 units. So, today, we'll start with earth processes. So everybody has the soft copy or hard copy of the book.
Yes.
Yes, sir.
Okay. So this block has a 4 unit. That unit one deals with the origin and formation of the Earth, the formation of our solar system, the planetary differentiation have been explained in this. Then the composition of the Earth, the core, mantle, crust, atmosphere, hydrosphere, about the how the Earth originates, and all those discussion will be in unit one. Unit 2 will deal with the plate tectonics, a thorough explanation on the movement of lithospheric planet, mantle convention, and planet tectonics will be discussed. The major plates, boundaries, hot spots are also will be explained. And unit 3 will deal with earth surface processes that like the river, wind, glaciers, and the coastal process, the transportation, and the erosion. All those things will be discussed in unit 3. Then unit 4 will deal with rock and minerals. So these are the 4 units that we are going to discuss today. So coming to the unit 1, the unit 1 talks about the origin and formation of the earth, how this earth formed. So our universe, which is almost 13.8 billion years old, is an outcome of commonly accepted Big Bang theory. The universe broadly comprises galaxies and stars. Our solar system is part of this galaxy Milky Way. So our solar system, the solar system which consists of the Earth and all other planets, these are the solar system is a part of the complete Milky Way or the galaxy. The Milky Way galaxy probably comprises tens of billions of other solar system similar to ours. There are other solar system also, which some we know and some we don't know, but they exist. And our solar system is part of this system, part of this total galaxy or the Milky Way. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, which revolve around the Sun. We know that in our system. And the Pluto was previously it was considered as a planet, but later on it was a dwarf planet, so it is not now been considered as a planet. So, or 8 planets they are and differentiated into two types. One is inner planet, and one is outer planets. So it is important to know about the solar system and how it came to existence. It is also important to understand the formation of the planet. In this unit, we will learn about the solar system and its components, the different components of the solar system, how it formed with time, how it evolved. Those will be discussed. To be precise about Earth and its attributes, the structure and the composition of Earth, thermal, magnetic, and gravitational field of Earth, atmosphere and hydrosphere of Earth. So, how the atmosphere comes into existence, how this gravitational field, which we talked about, Earth has gravitational field as well as magnetic field, how it arises, how the thermal temperature difference across the globe, how it arises. Those things we will be discussing this. After reading this unit, you will be able to explain the formation of solar system. You will be able to describe the concept of inner and outer planets, explain the formation of Earth, discuss the internal structure of Earth, describe the gravitational, thermal, and magnetic field of Earth, and outline the concept and significance of geological time scale. So these are the basic things which you will learn after the end of this block. Solar system formation and planetary differentiation. The nebula hypothesis is the most commonly accepted hypothesis to explain the formation of our solar system. The nebulae were composed predominantly of hydrogen and helium gases, besides dust side material chemically identical to the materials found on Earth. The nebula was supposedly rotating slowly under the influence of gravity. So, what is this nebula hypothesis that we are discussing here? This slow rotation of the dispersed nebula led to the contraction because of the influence of gravity. The contraction further led to faster rotation of the material and finally flattening of the nebula into a disk shape. Gravity resulted in the accumulation of matter of the nebula at the center of giving rise to photosun, the predecessor of present sun. So before this sun exists, which we are seeing here, before that there was a protosun. The matter in that protosun condensed and its temperature also rose higher to million of degrees. This led to the nuclear fusion. Fusion, you know what is the difference between fusion and fission? So basically, there is the energy releases in the solar due to the nuclear fusion. In the nuclear fusion, where hydrogen atom combine to form helium. Partial mass of the photosun converted into energy released in the form of sunshine. Then formation of the earth and its internal structure. The internal structure means we are talking about its core, mantle, and crust. In this section, we will learn about the birth about the planet, the earth. Earth is composed of three layers: the core, the innermost layer; mantle, the middle layer between the core and the crust; and the crust, the outermost layer. Was Earth from its inception at about 4.56 billion years a differentiated body, or was homogeneous? There are many questions which need to be answered. Some of the questions already we have got the answer. The scientists, they have evolved with time and they have found the what are the reasons, what are the logics behind that. The oldest rock, 3.7 to 3.8 million years, have been found in the western Greenland. Rocks from South Africa, Western Australia, and the Great Lake region of North America are also dated at 3.4 to 3.6 billion years. The oldest dated minerals, tinny zircon crystal, is 4 to 4.2 billion years, are found in sedimentary rock in Western Australia. The Earth is no doubt probably formed by the accretion of planetesimals and other materials from solar nebula. The Earth was not and was hot and molten at its time of inception at the early stage. When the early stage was there, the initial stage, the Earth was hot and molten in state. The gravitational differentiation, formation of different layers of Earth, started around 4.4 billion years ago. The innermost layer is the core, followed by the intermediate layer mantle, and the outermost layer is the crust. The three layers are different in terms of physical and chemical property. The Earth's internal structure is proposed based on the seismic waves which behave differently in different layers depending on the composition and physical nature of these layers. The two types of seismic wave, the P, that is compression, and S, that is shear waves, travel at different speeds and are also reflected and refracted from the boundaries marked between the different layers through the earth. Iron, nickel segregated into the innermost core part, whereas the lighter material silicates from the uppermost layer of the crust. So in the crust, which are differentiating into three layers, in the crust, the iron, nickel, these are the heavy metals that are segregated into the innermost core, whereas the lighter materials like silicates form the uppermost layer. The intermediate layer had both light and heavy material, which formed the mantle. The lighter material also dissipated heat from the interior to the surface, thus cooling the earth. That's why the earth got cooled. Initially, it was a hot body, and later on, it got cooled with time. This heat transfer from the interior of earth to surface is also defined as primordial heat. The source of heat along with radiogenic heat is responsible for melting of mantle rocks, and it's identified as potential cause of plutonism and volcanism on earth till date. The differentiation process also lead to the formation of ocean and atmosphere. The internal and external geological process were also set and the face of the earth formed end to date is all it is changing. All this makes us believe that earth is a dynamic planet, means it is changing slowly, slowly, slowly. The Earth's core is composed of iron and nickel predominantly. This part of Earth is under extreme pressure up to 330 to 360 gigapascal. The core, which is confined between 2890 kilometer to 6370 kilometer, is further divided into inner core and outer core. It was possible to study the nature of the core with the help of seismic waves. The inner solid core extended from 5,150 km to 6,370 km, whereas the outer core, which is molten, extends from 2890 km to 5,150 km. The mantle is the intermediate layer sandwiched between the core and the crust. So mantle is the intermediate layer which is sandwiched between core and the crust. This layer extends from the base of crust, average depth of 60 to 80 km in case of continental crust and 5 to 10 km in case of oceanic crust, to 2850 km. The mantle is an important link between the core and the crust. The heat from the interior of the earth is transferred by convection in the mantle to shallow depth. It comprises materials intermediate in density between the materials of the core and crust. This all information has been possible through seismic wave data retrieved from different depths. Earth crust is of the topmost layer, which is the least dense compared to the mantle and core. It is further divided into oceanic crust and continental crust. So this is the diagram where you can see the structure of earth depending on the inner core, the outer core, and the mantle which are present. They have differentiated that with the depth, how the things are changing from crust, mantle, and core. Then composition of crust, mantle, and core. Then so once it get formed, or once you differentiated this into crust, mantle, and core, now we should know what is the composition of the crust and the mantle and the core. The enormous pressure and high temperature inside the earth make it impossible for us to venture inside the earth even up to a few meter. The underground mining has at the most been carried out up to 10 km in rare cases. Thus, the nature of the lower crust, mantle, and core material is assessed by indirect geophysical data. The nature of lower crust and upper mantle can be partially assessed by magmas which originate at this depth. The seismic wave data from different depths have been instrumental in dissipating the structure and composition of Earth to a satisfactory level. Once information of the pressure and temperature, gravitational, magnetic field, and composition of the different layers are assessed, the same conditions are replicated in the high pressure temperature laboratory where stability ranges of different minerals are assessed, and thus we get a fair idea of what is the material at the deeper earth is made up of. The velocity of P and S wave is vary in different layers of earth depending on the density of the rock which make up of these layers. The P wave velocity are higher for denser rocks. So they have given the table in which they have shown the different rock type, then the typical rock, what is the composition, then the velocity of the P waves and their density. As you can see, the density goes from 2.6 gram per centimeter cube to 3.3 gram per centimeter cube, going from granite rock type to periodite rock type. The velocity of P waves increases with increase in this density. Since the P wave velocity in upper continental crust matches well with the granite rocks, we conclude the continental crust comprises average granodiorite composition member of granite clan rock. The oceanic crust based on the matches with PUF velocity showed that it comprises of basaltic and gabbroic materials. The seismic waves also helped in identification of Morbic discontinuity, which is commonly addressed as moho, which divides the crust and mantle. At the moho, the wave velocity is 8 km per second. This shows The rocks beneath and mantle are denser compared to the crustal rocks. The mantle is 2850 km thick and extended from the base of the crust to 2890 km. The P wave velocity of 8 km per second shows that the upper mantle rocks are periodotites. The upper mantle comprises minerals such as olivine and pyroxene, which with a magnesium-rich garnet pyrope. The upper mantle extends up to 410 km from the moho. Then the lithosphere is the rigid brittle layer and encompasses the upper 100 km, comprising the crust and the upper part of the mantle. The base of the lithosphere is marked with a low velocity zone. It is the zone where low percentage partial melting takes place. This zone is identified based on the S waves, which decrease in speed owing to melts present in the zone. The low velocity zone also mark the beginning of asthenosphere, which is a ductile layer. The low velocity zone, that is the known as LVZ zone, extends up to 200 to 250 km below the oceanic crust, whereas it is poorly constrained beneath the stable continental craton. Then you have the transition zone. Similarly, different zones they have divided. The lower mantle beyond 670 km is relatively homogeneous up to 2890 km. At the core mantle boundary, 2890 km, a drastic changes in the velocity of P wave is encountered. A drop from 13 km per second to 8 km per second. The S wave do not pass through the area beneath the boundary, indicating it to be a liquid nature. Data indicate that outer core is liquid in contrast to the metallic solid inner one. Then the thermal field, magnetic field, and gravitational field of Earth. Thermal field of the Earth. Primordial heat and heat generated through decay of radioactive elements such as uranium, thorium. The most important source is the primordial heat, which is the heat given out since the inception and differentiation of Earth. The other important source of internal heat is the heat given out by radioactive element concentrated in the Earth. Convection is the most important process by which heat from the deep earth is convected to the shallower depths. The heat transfer in lithosphere is by the process called conduction. It has been possible to measure the temperature at the depth up to 10 km. The geothermal gradient is measurement of the change in temperature with increase in temperature this depth inside the earth. The geothermal gradient varies from place to place inside Earth. The average geothermal gradient is 25 to 30 degrees centigrade per kilometer in the crust. The geothermal gradient at depth have been inferred through the measurement made on lavas and rocks which solidified from these lavas. The figure 1.3 fairly indicates the geothermal gradient inside the earth. So here is the geothermal gradient going from the lithosphere, then the upper mantle the temperature is 1900 Kelvin, then the lower mantle temperature 3000 Kelvin, then the inner core the temperature goes up to 7000 Kelvin. Magnetic field of Earth. We learned in the preceding section about the structure and composition of different layers of Earth. The outer layer core is the molten layer of the Earth, which comprises iron and nickel. The Earth magnetic field is attributed to the molten outer core. The convective current in the molten outer core, which is composed of iron nickel, produced electric field, and thus a large geodynamo is created which produces the magnetic field, which has its effect not only inside the earth on its surface but extended up to earth atmosphere and also far into outer space. So here it is the in the diagram. It is a schematic illustration of the invisible magnetic field lines generated by Earth represented as dipole magnetic field. You can see in this picture figure number 1.4. Then gravitational field of Earth. The gravity of Earth is responsible for the moon in its orbit. Earth's gravity is responsible for our atmosphere. Earth's gravity is responsible for our feet on the earth. So it depends on many factors and is experienced differently at different location on earth. For example, an area on earth will have a strong gravity if it has more mass in the subsurface compared to the area with less subsurface mass. The GRACE means Gravity Recovery and Climate Experiment mission of NASA uses spacecraft to measure the variation in Earth's gravity. Gravity is a natural force in which things with a mass are brought towards each other. The more the mass of an object possesses, the more the gravity it exerts on the surrounding object. The reason everything is pulled toward the earth is the mass of the earth compared to the objects on it. Gravity was a major force in the evolution of early universe and its component. It was responsible for the formation of first star, galaxies, planets, etc. It was the reason Earth formed and differentiated into three layers: crust, mantle, and core. Then atmosphere and hydrosphere of the earth. So by now you know the different layers of the earth. You know what is crust, mantle, and core. Then you know the what is the how the thermal the uh, electric field and the gravitational field comes into existence. Now the atmosphere and the hydrosphere of the earth. The total water present on, above, the under earth comprises the hydrosphere, whereas the atmosphere is defined as the outer gaseous layer of the earth held intact by the gravity. The atmosphere and the hydrosphere are an integral part of the earth and evolved with time since the birth of earth around 4.56 billion years ago. The earth aggregated from smaller bodies like planetesimals, which contain volatile components such as water, carbon dioxide, and nitrogen. Some minerals making up rocks had volatiles locked up in them. These volatiles got released during various geological processes which segregated Earth into different layers. The volatile were continuously released through volcanic cavity, volcanism on the Earth's surface, which started since the inception of Earth. The present volcanoes at the various plate margin emanate volatiles such as water, carbon dioxide, hydrogen, carbon monoxide, and nitrogen. The water and other volatiles on Earth would have also been added through extraterrestrial bodies that kept hitting the Earth when it is formed. The initial Earth atmosphere and ocean were impacted more by voluminous bombardment of extraterrestrial bodies with the Earth, thus contributing to the various volatiles. The troposphere, the closest layer to the Earth's surface, is 7 to 20 km thick and contains half of Earth's atmosphere. It contains almost all the water vapor and dust in the atmosphere. So troposphere is the layer which is very closest layer to the Earth's surface. It ranges from 7 to 20 km thick and contain half of the Earth atmosphere. It contains almost all the water vapor and the dust particles in the atmosphere. The clouds are formed in this layer in the troposphere. The stratosphere starts from where the troposphere ends and is about 50 km above the Earth's surface. This layer, with abundant ozone, absorbs harmful radiation from the sun. The jet aircraft and the weather balloons fly in this layer. That is the stratosphere. The mesosphere begins at 50 km and extends up to 85 km. This layer is not well studied, and according to the scientists, meteors burn up in this layer. The thermosphere started from 85 to 90 km to between 500 to 1000 kilometer. These space shuttles fly in this zone, and the International Space Station orbit Earth in this layer. The exosphere, the farthest layer from the Earth's surface, is very thin with hydrogen and helium, and it's merged into outer space. Then the geological time scale. The geological time scale has been devised to understand the geological evolution of Earth regarding time. The International Geological Time Scale is prepared and regulated, updated by the International Commission on Stratigraphy under the aegis of the International Union of Geological Science. The International Geological Time Scale starts from at 4.56 billion years when the Earth formed to the present time. It records the evolution of Earth with geological events like um, hydrosphere and atmosphere. The most important basis of formulation of this scale is rocks, fossil record, and stratigraphic units. The International Geological Time Scale has been divided into eons, eras, periods, and epochs. The broadest division of the geological time scale is into the four eons, that is the Haden, Archean, Proteogenic, and Phaneogenic. So these are the some of these time about the time scale. So this is the unit one. So the let us sum up the what you learned from this unit one. The unit on the origin of formation of Earth deals with various aspects of Earth since its inception from the gaseous state to its present form. Earth is the only habitable planet of solar system. It is a planet which was born almost 4.6 billion years ago. The initial structure and composition differed from its present form and composition. The Earth has been broadly divided into three prominent layers: core, mantle, and crust. The crust, which is the most explored layer of Earth, is divided into continental and oceanic crust. The continental crust differs from the oceanic crust in terms of thickness, composition, and nature. The Earth oceanic crust is capped in by water. The hydrosphere of Earth comprises the total of the water present on, above, the under the Earth's surface. Earth has its atmosphere which developed over the last 4,600 billion years. Earth has a unique thermal, magnetic, and gravitational field. Put together, this made Earth a visible and unique planet for the sustenance of life. The geologists have recorded the events of evolution of rock and life on Earth, devised in the form of geological timescale, which encompasses the journey of the Earth from the inception to the present time. So there are some questions has been given here with answers. You can go through it. Once you read this, then you can you can read those questions and answers, and you can write and practice it. Then the plate tectonics, their structure we'll be discussing. The introduction. The surface of the earth that we see today is divided into regions submerged under water and elevated above the mean sea level. We call this vast tract of earth as ocean and continents. A curious intellect is eager to know about their origin, antiquity, and evolution. Historians, geographic, philosopher, and geologists have divided the earth into different named units. The idea about origin of earth and its supposed early history and evolution are still evolving as new information received from experimental petrology, chronology, geochemistry, and space probes spore. The mechanism through which the Earth's surface evolves is being closely monitored. The more expressive surface phenomena like earthquake, tsunami, volcanoes are best understood by learning the present day theory of plate tectonics. The quest for comprehending the forces governing the distribution of continent, ocean, mountains, plateau, earth resources, volcanoes, earthquake, river shifting, natural hazards are best understood by analyzing the process of plate tectonics. So now the formation of continents and the ocean basins. The appearance of our race on the planet is very recent phenomena in the 4.5 billion years old history of Earth. We are eager, like kindergarten students, to understand the process which shaped our present day landscape, as also the performance of these geographic entities, which we term as continent and ocean. As a layman, we all understand that the portion of the earth that are above the water level are termed as continents, and those which are submerged under the seawater are termed as sea or ocean. In this unit, we will try to understand the geological characteristics and the endogenic processes of Earth that created those two or evolving dynamic landforms, the continent. Majority of us believe that continent comprises a fundamental pre-permanent and rather characteristics feature of Earth. Satellites images of Earth vividly depict it is the blue planet. The picture tells us that majority of the Earth's surface is covered with water and a few patches of land pop up. Approximately 71% of Earth's surface is covered with water and the remaining 29% is land. Thus, continents are scattered masses on a planet that is largely covered by water. Interestingly, these isolated masses, which comprises a small fraction of the total Earth, are the places which supports terrestrial life, including the human population. Our general understanding is that continents are the large, discrete, and rather continuous masses of land jetting above the seawater. In geology, continents include the submerged continental itself, as also the icelands on the shelf, which have a similar crustal makeup. If we view continent as a cultural identity, then perhaps the nearby Iceland, which do not share the same geological features, are also grouped together, like Greenland with Europe or Madagascar with Africa. There are three broad continental grouping models: the fourth continental model, sixth continental model, and the seventh continental model. The modern day seven continent model recognizes North America, South America, Europe, Africa, Asia, Australia, and Antarctica as the seven distinct continents. The question that have always generated curiosity and discussion among scientists and public for a long time are: have the continents been there since the earth originated? Are there the results of some chances factors or natural luck which favored human evolution? Which forces sculptured the crust with its immense variation? Do the other planets in our solar system also have similar distribution of land and sea, as also similar crystal structure? Our present day understanding of the earth processes and the knowledge gathered through satellite and space probes reveals that perhaps our planet is unique.
পড়ে দেন পড়ে দেন
The low density of continental rocks is the primary reason for their elevation above the sea level. The continents, which dominantly comprises the continental crust, on an average rise above 125 meter above the main sea level. Further, approximately 15% of the continental area rises over the 2 kilometers the sea level. The highest point of the continental crust, the Mount Everest, rises 8,848 meter. These significant heights contrast markedly with the depth of the ocean floor, which averages about 4 kilometers below sea level. A direct consequence of these, of their being lined by dense oceanic crust composed mostly of basalt and thin veneer of sediment. The formation of continent crust has been continuous process throughout the Earth history. At the Archean and Proterozoic boundary, around 2.5 billion years ago, a distinct change in the rock record occurs. The composition of the upper crust before this break comprises a mixture of basalt and sodium-rich granites. This rock comprises the tonalite, uh, trongemite, and gradorite or TTG suit. The composition strategy differs from the present day upper crust, which is dominated by K-rich granites. This profound change in crystal composition appears to be linked to the changes in the Earth tectonic regime. Probably below 2.5 billion years, higher level of radioactive decay produced more heat in the oceanic crust, and it was hotter, thicker, and more buoyant and could not subduct. As a result, denser crust melted and resulted in the production of sodium-rich igneous rock of the TTG suit. Plate tectonics, as we comprehend today, began operating after the late Archean, when the oceanic crust becomes cooler, lost its buoyancy, and could thus sink back into the mantle. From this time, the relative height of the ocean basin and continental platform has remained relatively static. At the beginning of the Proterozoic eon, about 2.5 billion years ago, the crust had already gained much of its present setup. Then the question, Earth is a blue planet. In fact, it is the only known planet with sea of liquid water on its surface. The total amount of water on Earth has been estimated to be around 1335 million cubic kilometers. Out of this water, ocean contains about 97.2%. Ice caps keeps 2.15%, while 0.65% is the available fresh water. Ocean and sea cover over 70% of the Earth's surface. There are two aspects of origin of ocean. First, the origin of ocean floor, and second, the origin of ocean water. The oceanic crust is dominantly different from the continental crust. The process of formation of oceanic floor occurs at mid-oceanic ridges. Throughout the center of the major oceans runs an interconnected ridges system which have been termed as the mid-oceanic ridge. A crack-like valley run along the crest of this ridge system. Seismic investigation along with the ridge axis suggests that the two sides of the ridge are moving away from each other. As the crack widens, hot molten rock material from the below pours out and solidified into the crack. The molten rock material is dominantly basaltic in composition and contains iron bearing magnetic minerals like magnetite. These minerals orient themselves along the prevailing magnetic field of the earth. Thus, the new oceanic lithography is oceanic lithosphere is magnetized in the direction of the ambient magnetic field of earth. We know that the magnetic field of the earth has been changing throughout its 4.5 billion year of history. For the past 7 lakh years, the north magnetic pole has been close to its present position. The speed of spreading of either side of the mid-oceanic ridge varies from less than a centimeter per year to about 8 centimeter per year. The East Pacific rise records the fastest spreading rate, while as the mid-Atlantic ridge and the Calcibric ridge of the Indian Ocean are the slowest. At convergent plate boundaries, the oceanic lithosphere subducts beneath the continental plate. Such regions mark the zones of consumption of the oceanic crust. This destruction of oceanic lithosphere explains the absence of sediments above 150 million years old on the western floor. The general phrase used in this context is the tea in the cup is older than the cup itself. This can be explained because the older sediments accumulated on the ocean floor have been carried away with the plate and are chaotically piled up at the edge of the continent or are carried down along with the subducting oceanic plate and consumed in the mantle. The second aspect of the formation of ocean relates to the origin of oceanic water. The origin of ocean has to be traced since the time of the Earth formation, that is the 4.5 billion years ago, when the process of Earth accretion through planetesimals started. There could be three likely source for the water. It could have either separated out from the rock that make up the bulk of the earth, or it could have arrived as part of the late accretion mineral of the water-rich
कितना जगह
minerals similar to the carbonous chondrites that we
या पानी
observe today, or is
दिया
we could have been added as a part of the late accreting veneer of the icy planetesimals of or comets.
वही कौन सी मोह है सकता ये ले
The composition of the oceanic of ocean offers some clues as to its origin. Space scientists have studied the isotopic composition of frozen water in comets Halley and Yakutske. They suggest that if all the comets contain the same water ice, then comets cannot have delivered all the water in the Earth ocean, as the isotopic composition of both is different. Further, the meteorites could not be considered as the source of the entire water on land, as it would have resulted in a high concentration of xenon in Earth atmosphere. The search of source of water in ocean is an active area of research. They require more studies about comets and other planets. Current state of knowledge suggests that most acceptable hypothesis for the source of the ocean water is a combination of water derived from comets and water that was caught up in the rocky body of the earth as it formed. The mixture satisfactorily explains the low xenon concentration and the deuterium concentration.
हरा ही मुर्गी मुर्गा
Sea floor spreading, evidence and mechanism.
बाहर लाइट लगी
Floor spreading occur at the mid-oceanic ridges, which topographically are long mountain ranges extending through the middle of the every ocean floor. A ridge forms along a crack in the oceanic crust. At a mid-oceanic ridge, because of the extension of the crust, the oceanic crust thins out and develops cracks and fractures through which molten materials rises from the mantle and erupts. The molten rock material then spreads out, pushing older rocks to both sides of the ridge. This process called sea floor spreading continuously adds fresh materials to the ocean floor. The driving force for the continental drift and sea floor spreading was initially explained based on the convention current hypothesis. The interior of Earth is hot owing to the primordial heat related to the genesis of Earth, as also because of the radioactive minerals and immense pressure of overlying rocks. It has been postulated that heat transfer from the interior of the Earth to the surface results in the formation of huge convection current cells in the mantle, which fuels the crystal movement. The region where two upwelling adjacent hot convection current cells come near the surface is the site of formation of new oceanic crust. Subsequently, as scientific understanding advanced, the theory of plate tectonics developed. Then the plate tectonics. Plate tectonics is the theoretical scientific model which tried to explain the large-scale motion of seven large plates and many small plates of the Earth at a lithosphere over the past hundred of millions of years. The theory builds on the concept of continental drift, the idea proposed by Wagner in 1912. The plate tectonics theory was largely accepted in the 1970s after the validation of the seafloor spreading theory and inputs by many workers as details below in the section on brief history. Definition: the theory of plate tectonics states that the surface of Earth comprises rigid plates which behaves as brittle solid and travel on a viscoelastic or plastic layer termed as asthenosphere which deforms readily by creep. Then brief history. Brief history you can go by you can read by your own. Then the major plates. Our planet Earth has a three-layer structure. Crust is the outermost layer, which is followed by mantle, and then the innermost layer is the core. The lithosphere, which is the outer rigid layer, is made up of numerous rigid brittle fragments termed as tectonic plates. These tectonic plates move like a ship on the asthenosphere. The asthenosphere is highly viscous, mechanically weak, and plastically deforming region in the upper mantle. It lies below the lithosphere at a depth of approximately 80 to 200 km below the surface of Earth. The zone is characterized by sudden drop of seismic wave velocity and is termed as low velocity zone. The lithospheric plates are made up of dominantly continental crustal material or the denser oceanic crustal material. At a plate boundary, the interaction between the two plates is interplay of their densities. The denser oceanic plate usually subducts beneath the higher continental plate at a continental plate oceanic plate collision boundary. The lithospheric fragments, which are larger than the 20 million square kilometer, are termed as major plates, and those between 20 million square kilometer and 1 million square kilometer are termed as minor plates. So here they have discussed what are the major plates. In the major plates, they have Pacific plate, North America plate, Eurasian plate, African plate, Antarctic plate, Indo-Australian plate, and South American plate. In the minor plates, they have Somali plate, Nazca plate, and the Philippine Sea plate, Arabic plate, then Caribbean plate, Cocos plate, Caroline plate, Scotia plate, Burma plate, New Hebrides plate. Then the movement of lithospheric plates. There are three kind type of the movement of lithospheric plates creates three type of plate boundaries. They are convergent plate boundaries, divergent plate boundaries, and transform plate boundaries. Convergent plate boundaries are or destructive boundaries or active margins occur where two lithospheric plates move together towards each other to form either a subduction zone or continental collision zone. Similarly, the divergent boundaries or constructive boundaries occur where two plates move apart from each other. If they move close to each other, then that is convergent plate. If they move away from each other, then they are called divergent plate. And here they have shown a sketch showing the convergent plate boundary. They have shown it here. Then the mental convention and plate tectonics. Plate tectonics model tries to explain the tectonics of Earth based on the plate movements. The theory assumes that plates are the rigid, brittle part of lithosphere which travels as ships on a weak layer at the asthenosphere. The tectonic plates are composed of oceanic lithosphere and thicker continental lithosphere, each topped by its characteristic type of crust. Divergent plate boundaries are the mid-oceanic ridges and continental rifts where new lithospheric is being created. Convergent plates boundaries are the zones where the denser plates is being consumed. So this is the sketch showing the convention current in the mantle in relation to the plate boundaries. There's the inner core, then the outer core, then you have the asthenosphere, the mantle where you have trench, ridge, lithosphere, plate boundaries and hotspots. There are two views regarding their origin. One suggests that hotspots are because of mantle plumes that rise the thermal diapers from the core mantle interface. The other theory suggests that lithospheric extension permits the passive rising of the melt from the swallow depth, and that mantle occurs is not the anomalously hot. So the Earth is a blue planet. It is the only planet in our solar system which supports life throughout a long eventful history of 4.5 billion years. The various endogenic forces operating on the planet created the continents and the ocean. The geographical entities are ever developing and dynamic. The continents, as we know today, had an entirely different location about 335 million years ago. These have been converging and diverging during the different time span in the history of Earth. The theory of continental drift, sea floor spreading, and the plate tectonics have tried to scientifically explain the processes and probable mechanism of the movement of continents and opening and closing of ocean basins. The role of mental convention and hotspots in the fueling the global movement of lithospheric plates and volcanism is interesting. So this ends the two that unit 2. Then we will go to unit 3. We'll take a 5 minutes break. Then we'll start unit 3 and unit 4. Thank you.
Hello. Hello, Chandan sir. Hello. Hello.
Hello, ma'am.
Chandan sir. Hello.
Hello.
Chandan sir କହୁଛନ୍ତି?
Hello, ma'am. Ma'am, କୁହନ୍ତୁ।
ଏକ୍ଜାମ କଥା ଗୋଟେ
Repeat again, ma'am.
ଏକ୍ଜାମ କେବେ ଜାଣି ହଁ ଏକ୍ଜାମ କେବେ ହବ ଜାଣିଛନ୍ତି?
ମ୍ୟାଡ଼ାମ କୋଉ ଏକ୍ଜାମ ଟା କହୁଛନ୍ତି? ଡିସେମ୍ବର ଏକ୍ଜାମ କି?
ଏଇ ଆମର ହଁ ହଁ
ସେଟା ଡିସେମ୍ବରରେ ହିଁ ହବ।
ଡିସେମ୍ବରରେ ନାଇଁ?
ଆଜ୍ଞା ମ୍ୟାଡ଼ାମ।
ଆପଣ କଣ ଆପଣ କଣ କରନ୍ତି?
ମ୍ୟାଡ଼ାମ ମୁଁ ତ ଏବେ ପଢୁଛି ନା।
ଏଇଠି ବିଏସି ପରେ?
ଆଜ୍ଞା ମ୍ୟାଡ଼ାମ ବିଏସସି ପରେ କମ୍ପ୍ଲିଟ ନେକ୍ସଟ ଏମଏସସି।
ଟିକେ ଫୋନ ନମ୍ବର କଣ୍ଟାକ୍ଟ କଲେ ଟିକେ ଭଲ ହୁଅନ୍ତା। ମୁଁ ଜାଣିପାରୁନି ତ ଟିକେ ଇନଫର୍ମେସନ।
ମ୍ୟାଡ଼ାମ ଆମର ହ୍ୱାଟ୍ସଆପ ଗ୍ରୁପରେ ଜଏନ୍ ହେଇନାହାନ୍ତି କି? ଓକେ ମ୍ୟାଡ଼ାମ ନମ୍ବର ଟା ନେଇ ନିଅନ୍ତୁ ଆଉ ମେସେଜ କରିଦେବେ ମୁଁ ଜଣେଇଦେବି।
କୁହନ୍ତୁ।
7895
So I'm back. So we'll start with the unit 3. So unit 3 discusses the surface processes. So one is the erosional agent. The erosion is defined as the geological process in which the worn out earth material are transported by natural agencies such as wind, river, and rain. The natural forces such as wind, water, and ice. These natural agents or agencies come into play individually or together and erode and transport material from one place to another depending on many factors such as energy of the eroding agency to carry transport the worn out earth material. Erosional agents are responsible for changing landscapes. The mountain peak can get flattened as a result of erosion over millions of years depending at the rate of erosion. Similarly, low-lying areas can accumulate the eroded materials and can transfer into new landscape. Then weathering. How do we define weathering? Weathering is breaking of surface rock into sediments by any natural process. Sediments results from the weathering of a pre-existing rock by either mechanical, physical, or chemical weathering. There are weathering can be mechanical weathering, weathering can be chemical weathering, or it can be also physical weathering. The physical weathering involves breaking of rock and no change in the composition of rock. Physical weathering implies the breakdown of rock because of the extreme temperature change, widening of cracks and crevices of rock, exfoliation. The chemical weathering involves a reaction between the rock and the environment, rainwater, river water, sea water, etc. Both physical and chemical weathering generates sediments. The weathering rocks can result by thawing and freezing of water in cracks and crevices in rocks in cold area, by splitting the rock because of deeply penetrating roots of trees continuously passing the stream river over rocky terrace, moving glaciers over rocks, etc. Then the transportation. The sediments formed by the weathering are eroded by river, wind, and glaciers to sedimentary basins. The journey of the sediments may take long to reach the destination. For example, the load of sediments accumulated by river may rest finally in the deltas formed at the mouth of the river. The accumulation of sediments at the base of a hillock is another example of transportation of sediments because of gravity. The moving of boulders by a glacier is an example of transportation by the moving ice. The high velocity wind can carry, sorry, the high velocity winds can carry on fine sediments or far off places and drops them when the winds get milder in terms of velocity, and those can cause formation of heaps of sand or even sand dunes in the desert areas. Oceans are the greatest repositories of all kinds of sediments brought by the river and the wind. The current in the river and the wind are responsible for the transportation of sediments. The river-borne sediments contribute annually around 25 billion ton to the ocean. Then deposition. It is the process which is the outcome of water wind current or mass wasting putting the sediments to rest. The powerful water or wind current may deposit heavy sediments like gravels closer to the source, but they can carry on with the lighter sediments such as sand and clay to far off places. On the weakening of river and wind currents, they will deposit the land load of sand and clay. The changing intensity of the current also help in sorting of the sediments with the heaviest deposited close to the source and the lightest carried far away from the source. The mass wasting allows the deposition of sediments at the base of slope. Then diagenesis. It is a sedimentary phenomena where the sediments undergo physical and chemical changes mainly triggered by pressure. Fluids trapped in sediments are expelled and heat and chemical reactions cause lithification and formation of sedimentary rock. Deposition features formed by rivers, winds, glaciers, and coastal processes. Stream erosion, transportation, and deposition. Stream water is one of the widely acknowledged natural agencies which contribute to erosion, transportation, and deposition of sediments. The important erosional and depositional features created by running water of streams are prominent features of Earth. The streams mostly originate in mountains and are in the youthful stage. The headward waters of the youthful stream leads to the formation of V-shaped valley by cutting deeper across the bottom of the sideways solid rock. The V-shaped valley formed by erosion and the eroded materials is carried by the stream, causing further degradation of the bedrock. Most of the sediments get temporarily deposited along the stream course in the form of bars, floodplains, deposits. The continuous repeated flow of water in streams may carry these temporarily deposited sediments to the final resting destination, such as alluvial fens and deltas, where river ends into a sea or an ocean. Glacial erosion, transportation, and deposition. It is a moving mass of ice which is formed on land by compaction and recrystallization of snow. In this unit, we will study about the valley glacier, which, like a river, flows from higher or lower altitude under the control of gravity. The rate at which glacier move can be variably from the less than a few millimeter to 15 meter a day. The glaciers move fast if the slope is steep. A U-shaped valley formed by glacial erosion is contrast to a V-shaped valley by the river erosion. The glaciers have power to erode the bedrock over which it creeps. The rock under the glacier is easily abraded when the meltwater enters the cracks in the bedrock and freezes. The continuous percolation of meltwater through the cracks and its freezing leads to the breaking of the bedrock. The loose bedrock fragments are plugged by the base of the moving glacier. The process of eroding the bedrock is known as plucking. And the thick glacier movement over the bedrock also leads to the grinding and crossing of the rock. The grinding of rock leads to the formation of rock floor, fine powder resembling the floor. It comprises silt and clay sized particles. The boulders trapped in the glaciers also get faceted during the movement of the glaciers. Wind erosion, transportation, and deposition. Wind is an important natural agent of erosion, transportation, and deposition. The loose, dry, and disposed finer sediment can be easily removed and carried by wind and cause deflation. The deflation is in some areas is commonly known as blowout. The wind velocity dictates the erosion and transportation of the sediments. The high velocity wind can move sediments easily and to a greater distance. The sand, which is heavier compared to the silt and clay, is carried by wind close to the land surface. Sand moves by saltation created by the wind current. Sandstorms can result because of the top speed wind. The suspended sand in the wind near the land surface can sandblast surfaces on hard rock in its way. The wind-blown deposits can form emerging landforms, loess and sand dunes. Loess deposits comprises angular grains like quartz, feldspar, clay mineral bounded by calcite cement. Sand dunes, on the contrary, contain rounded sand grains, mostly comprising quartz mineral. Sand dunes are typical of a desert terrain where heaps of loose, wind-blown sand accumulate and form mounds of distinct shapes. The sand found in sand dunes is well sorted and almost devoid of silt and clay. Sea wave erosion. So erosion can be taken place by wind, also can be by river and now by sea. The sea wave erosion, transportation and deposition. A sea wave is an important natural agent which can shape of the coastal areas or areas adjoining the sea. It is a powerful agent of erosion, transportation and deposition. The sea wave can erode whether the coastal areas or build up the coastal areas. Before going further, let us define a sea wave and how it is driven. The moving wind over the vast open expanse of the ocean and seas creates a wave in the ocean and the seas. The wind created waves have the energy to erode the coastal rocks. The sea waves have the energy to transport and deposit sediments in the coastal areas. Erosional features sculpted by the sea waves are remarkably interesting and quite unique. A beach is a depositional features formed by an accumulation of sand and gravel. The exposure of sand deposits on the beaches is controlled by rising and falling tides. Beach is part of the coast. Coast is extensive, comprising beach and a band of land inland from it. Coast can vary from wide, gently sloping plains to rocky terrains and cliffs. In this unit, we have touched upon the basics of weathering, transportation, deposition, burial, and and diagenesis. The unit discusses the external natural agencies such as river, wind, glaciers, and sea waves, which have helped to shape the faces of Earth to a great extent. These natural agencies have the powers to weather the rock, transport the weatherland materials and of various size, and deposit the weathered materials at viable places. The erosion of material can lead to sculpturing the earth surface affected by such activities. Similarly, the eroded materials are carried to different spots and laid off depending on the transporting ability of the natural agency. The final resting of the transported material further affects the face of the earth. So, in the earth processes, they are the natural processes such as magmatism, volcanism, blowing wind, flowing water, moving ice, or glaciers that occur within and on the earth and are largely responsible for shaping the earth. Then, what is the potholes? It is a depression formed in the riverbed by the abrasive nature of the boulders, gravels, sands. Then what is distributary? The main river water is distributed into a small shifting channel when it deposits sediments load in the mouth of the river during a delta formation. Then Badfoot Delta, stream sedimentation that forms the finger-like distributaries resembling the bird's foot, thus the name foot delta. Headland, a thin piece of land that ventures from a coastline into the sea. Mass wasting, a process by which soil and regolith and rock move downslope under the influence of gravity. Then point bar, a depositional feature characteristics of a meandering river. The inside band of the meandering river commonly accumulate sediments giving rise to the point bars. Then rock cycle, change over from the one key rock type to another igneous, sedimentary, and metamorphic through the geological processes and geological time. Saltation, the transport of hard particle over an uneven surface by air or water. Then now we will come to the last unit, that is rock and minerals, the unit 4. So you have read about the earth surface processes in the previous unit. In this unit we will study about the rock and mineral. A rock is composed of combination of some minerals, hence minerals are the building block of rock. Some rock contain only one kind of minerals, whereas some other contain several kind of minerals. Geologists should study rock and minerals to understand the exogenic and endogenic processes and events that occurred in geological past at some specific part of the earth. The specific rock and minerals occurring in particular geological environment also help them to locate potential deposits of economically important resources. In this unit, we will learn about minerals and their importance to human being. We will first introduce minerals and then discuss about the chemical and structural classification of minerals. We will further discuss about the characteristics of common rock forming mineral groups, weathering and basic concept of geochemistry. First, minerals. You find that sand contain grains of various colors. What are they? They are different minerals making up sand. You must wonder how we identify these minerals. We can identify minerals based on their physical property. The branch of geology that deals with the minerals, their structure, composition, occurrence, and association is termed as mineralogy. We define a mineral as a naturally occurring inorganic solid, crystalline substance having specific chemical composition. Now we will discuss each aspect of the definition. Natural occurring. A substance can be called a mineral only when it is found in the nature and is not produced artificially. Substances synthesized or produced in the laboratories does not qualify to called as a mineral. Inorganic. Only the substances formed by the inorganic processes qualify to be called minerals. Then solid. Liquid and gases do not qualify to be called mineral except the native mercury. Crystalline substances. Solids without form does not qualify to be called as a mineral. Only the solid substances which are commonly crystalline but not always can be called as mineral. Specific chemical composition. Uniqueness of mineral comes from its chemical composition and the arrangement of its atoms in the internal structure. Chemical composition of a mineral is fixed or it ranges within a particular limit. Minerals are formed by different geological processes under various physiochemical conditions in nature. These natural physiochemical conditions are determined by the concentration of the chemical component, temperature, pressure, and the interaction of minerals with existing rock. This happens in a cooling magma, molten rock material in earth interior, or lava, molten rock material at the earth surface. But it can also take place in evaporating fluids such as water. We can group them as follows. Let us now define the processes under which the mineral can form. One is crystallization, one next one is evaporation, then your precipitation, then metamorphism. Crystallization, it takes place during the cooling of molten mineral materials. Evaporation, when a solution evaporates, the solute stands behind, which is an element or compound, as the mineral, halide or table salt. Precipitation, when a mineral precipitated from a solution such as the calcite from calcite saturated groundwater in a cave. Metamorphism, this takes place at a high temperature and pressure when new crystals have grown in solid materials such as diamond from coal and metamorphism. Minerals play a significant role in our life. Just to name a few, like edible salt, which is derived from halite mineral, that is NaCl, to the utensils we use, which comprises metals like steel or aluminum or copper. These metals are derived from different ore, which are minerals, ceramic mugs, glass tumbler, battery, filament of light bulb, etc. All are made from various minerals in some or other form. You people are listening?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. The bricks, cement, tiles, and paints which we use in the construction of our houses, all of them make up minerals. We will appreciate knowing that different components of the automobile, computers, mobiles are comprise various minerals. Even toothpaste, automobile fuel, lead of pencil, mirror glass, cosmetic we use, the jewelry and the gems we wear are all minerals. Now the chemical classification of mineral. Mineral can be classified based on their chemical composition and crystal structure. However, majority of the mineralogists prefer to classify minerals into families or groups based on their chemical composition. One is native elements. This include the category of pure metals. Nearly 40 chemical elements occur in nature as relatively pure minerals and in native state. Carbon, sulfur, copper are often found in native state. Silicates. Silicates form the largest group of minerals on Earth crust. Most rocks are composed of 95% silicates. Silicates are composed largely of silicon and oxygen along with addition of ions such as aluminum, magnesium, iron and calcium. Further, in this section, we will read about important rock forming silicates like feldspar, quartz, olivine, pyroxene, garnet, and micas. Oxide. This group ranges from dulls, ores like bauxite to gems like rubies and sapphires. The most widespread mineral of this group are oxide of silicon, aluminum, iron, manganese, and titanium. Common oxides include hematite, magnetite, chromite, ilmenite, and rutile. The oxide class also include the hydroxide minerals. Sulfides. Sulfides are made up of compound of sulfur, usually with a metal. Many metal ores belong to this group like pyrite, ferrosulfide, or copper sulfide, lead sulfide, zinc sulfide, galena, that is lead sulfide. Many sulfide minerals are economically important as metal ores. Then sulfate. They are made up of compound of sulfur combined with metal and oxygen. Sulfate commonly formed in evaporite settings where highly saline water slowly evaporate, allowing the formation of both sulfate and halides. Common sulfate include calcium sulfate, barium sulfate, and strontium sulfate. Halide. They form from halogen elements like chlorine, bromine, fluorine, and iodine combined with metallic element. They are incredibly soft and easily dissolved in water. Halite, that is NaCl, is a well-known example of this group. Then carbonate. They are the group of minerals made up of carbon, oxygen, and a metallic element. The carbonate minerals comprise those minerals containing the anion CO3 2 minus and include calcite, aragonite. Then the phosphate. This mineral group include any minerals with tetrahedral unit of AO4 where A can be phosphorus, antimony, arsenic, or vanadium. Then structural classification. We have read that silicates are the most abundant minerals in the earth crust. They are composed of oxygen and silicon, which are the most abundant elements found in combination with the cations of other elements. We can classify silicates based on their structure. The basic building block of silicates mineral structure is Si4 minus in the silicate ion, which is formed by four oxygen that surrounded the share electron with a silicon ion. This four-sided pyramidal form known as tetrahedron. Each side of the tetrahedron form a triangle. The silicon oxygen tetrahedron is an anion which has four negative charges. The negative charges must be balanced by four positive charges to make the electrically neutral mineral, which may happen in the following two ways. The ion can bond with cations such as sodium, potassium, calcium, magnesium, or iron, or the ion can share oxygen with other silicon oxygen tetrahedron. So this is the structure model of the silicate tetrahedron, which has one silicon ion shared by four oxygen. We classify the silicate minerals based on how the silica tetrahedron are linked. Tetrahedra may be isolated or be linked in rings, single chain, double chain, sheet, or framework. Nesosilicate, independent or isolated tetrahedral group. The isolated tetrahedra are linked by the bonding of each oxygen ion of the tetrahedron to a cation. Then sorosilicates. double tetrahedral group. In this type, two tetrahedra linked by a single oxygen atom or two tetrahedra share one oxygen. The ratio of oxygen to silica is 2 is to 7 or 3.5 is to 1. Example of the silica structure is epidote or melalite, melilite. Then cyclosilicates, ring structure. Each of the three tetrahedra sharing oxygen ion, such as mineral beniotite or mineral exinite or mineral beryl. Then ionosilicates, single chain silicate SiO3 2 minus, double chain Si4O11 6 minus, then pyrosilicates Si2O5. So all there are silicon oxygen, and oxygen is bonded with another silicon atoms. So then the tectosilicates SiO2 three-dimensional framework form when each tetrahedra shares all its oxygen with other tetrahedra. In this silicate structure, the ratio of oxygen to silica is 2 is to 1. So these are the different structures that have shown it in this diagram for the silicates, the new silicate, sorosilicate, cyclosilicate, single chain, double chain, polysilicate material, and tectosilicate. Some of these minerals are the essential component of the rocks are called essential minerals, and others are called accessory minerals. The most common rock forming minerals have been discussed. Then silicates. Silicate minerals are the most important rock forming minerals and are building block of the common rock forming minerals. Silicate minerals make up about 90% of the rock in the earth crust. The common rock forming silicate minerals are grouped as mentioned below: olivine group, garnet group, pyroxene group, amphibole group, mica group, feldspar group, and silica group. Then the first one is the olivine group. Olivine is the name of group of common rock forming minerals mostly found in dark colored mafic and ultramafic igneous rock. It is a magnesium ion of silicate with the following chemical composition: XY or 2SiO4, where X is iron and Y is magnesium. Olivine group of minerals are usually green and have composition that typically range between Mg2SiO4 and Fe2SiO4. The ratio of magnesium and iron varies between the two and members of olive group. Olivine is not a separate mineral, and the term is used instead of potassite or phthalate. Then garnet group general composition is X3Y2 SiO4 whole 3, where X can be calcium, magnesium, iron, manganese, and Y can be aluminum, iron, manganese, vanadium, and chromium. Minerals of garnet group are used as gemstones and abrasives. Then pyroxene group of minerals are the most significant and abundant group of rock forming ferromagnesium silicates. Pyroxene crystallize in both orthorhombic and monoclinic crystal system and occur in stubby prismatic crystals. General formula is XYZ2O6, where X is different cations like sodium, calcium, manganese, iron, magnesium, lithium. Y is manganese, iron, magnesium, iron, aluminum, chromium, titanium. Z is silicon, aluminum. Then amphibole group. The most common amphibole is hornblende. Hornblende is quite like agatite in the both and dark minerals. However, hornblende crystals are longer, thinner, and shinier than the augite. Augite. Then the mica group. It has also general formula where XY, X2, Y4, and Z8, O20. Then the feldspar group. Then the silica group. There are different groups depending on the structure. Then rock. These rocks are sometimes hidden deeply beneath our feet by soil cover, and sometimes they are exposed on earth's surface when we can see them. Rocks have been fascinating human beings since time immemorial. Stones were among the first tools and weapons used by humans. The rock caves provided shelter to the prehistoric man. He could ignite a fire by rubbing piece of rock. Rock have been and are being explored by men for extraction of metal, minerals, and building materials. Later, metal became the basic of wealth and the foundation of empires. Coherent minerals are held in a rock together and can be separated back. A pile of unattached mineral grains, loose sands does not constitute rock. Naturally occurring. For geologists, in occurring natural material brick do not qualify under this natural occurring rock. Then aggregate of minerals or a mass of glass. You have monomineralic rock and polymineralic rock also. The identity of a rock is determined partly by its mineralogy and partly by its texture. So there are different kind of rock. Classification of rock. There is igneous rock, sedimentary rock. Then you have metamorphic rock. Sedimentary rocks comprise of grain of sediment that have resulted from the weathering and disintegration of the pre-existing rocks. Sedimentary rocks may be layered and may also contain fossils. Metamorphic rocks are formed when a pre-existing rock is subjected to heat and or pressure. They may show evidence of recrystallization resulting in the formation of bigger crystal, bending of minerals, or foliation can be seen. Then the igneous rock. Igneous rock are formed by cooling and crystallization of hot molten material called magma, which rises from the mantle inside the earth and cools. This cooling may happen either below or on the surface. When melted rock material is below Earth's surface, the cooling is slow. It takes a long time to cool, resulting in coarse-grained igneous rock. When melted rock moves above the Earth's surface, that is the lava, it does not take long to cool as it is the contact with air and water. It cools rapidly and gets less time for growth. Therefore, the rocks are fine grained. They may have air cavities, showing that gas has escaped from the site of the release of pressure. In extreme cases, they may appear glass like. The igneous rock may be intrusive or extrusive. Intrusive igneous rock, and also there's also extrusive igneous rock. Three types of igneous, based on their mode of occurrence, have been identified. That is the plutonic rock, volcanic rock, and hyperbasal rocks. Then the sedimentary rock. Sediments are produced by the weathering, either physical, chemical, or biological, by geological agents such as wind, river, glacier, ocean, groundwater. Therefore, they are categorized as secondary rocks. The sedimentary rock is a rock that forms at or near the surface of the earth in one of the several ways by the cementing together of a loose crust that had been produced by physical or chemical weathering of pre-existing rock, by the growth of cell masses or cementing together of cells and cell fragments, by the accumulation and subsequent alteration of organic matter from living organism, or by the precipitation of minerals from the solution. The loose grains of the sediment transform into sedimentary rock by the following five steps, that is, weathering, then erosion, then transportation, then deposition, then lithification. The sedimentary rock may be classic, classic, clastic sedimentary rock, or it is non-clastic sedimentary rock. They can also be differentiated into clastic and non-clastic sedimentary rocks. Then metamorphic rock. Metamorphic rock make their name from the Greek word meta meaning change and morphe meaning form. A metamorphic rock is one that form when a pre-existing rock or protolith undergoes a solid state change in response to the modification of its environment. This process change is called metamorphism. The formation of metamorphic minerals and textures take place slowly. It may take thousand or million years. The most common processes are recrystallization, phase change, metamorphic reaction or neocrystallization, pressure solution, plastic deformation. Then weathering. Weathering can also be defined as a set of physical, chemical, and biological processes that break down rock and minerals into crust or to create sediments, new minerals, soil, and dissolve ions and compounds. There are three processes of weathering: physical weathering, chemical weathering, and biological weathering. Then factors controlling the weathering: the parent rock, the nature of the parent rock, the topography, the structure, the climate. These are the factors, and the presence or absence of soil, the time of exposure. So these they control the weathering. Types of weathering: there is physical weathering. It involves the mechanical breakdown of minerals and rocks by variety of processes, and physical weathering is also known as mechanical weathering. Rocks can physically break because of a variety of reasons. These reasons are temperature, then the pressure release, abrasion, then the freeze throw. These are they are responsible for this, and the frost heaving also, the hydraulic action also, then the action of gravity. They are responsible for physical weathering. Then chemical weathering, you have already been introduced to chemical weathering earlier in this section. It occurs when the minerals react with air or water. In this chemical reaction, some minerals dissolve while some combine with water and atmospheric components such as oxygen and carbon dioxide to form new minerals. Chemical weathering has a special place in weathering process, as water along with other chemicals and dissolved gases may enter even in thin cracks produced by physical weathering or along bedding and joint planes. With time, these cracks and joints are widened and more percolation along them, leading to the faster chemical weathering. In the chemical weathering, decomposition takes place by bonding with the removal of cations from the solid mineral surfaces. Water plays an important role and is highly effective in dissolving many substances. Chemical weathering involves the following reaction: one is dissolution, then the carbonation, then oxidation, then hydration, then spherical weathering. It is explosion, exfoliation of is cracking or stripping of a rock body, which occur mainly because of physical mechanical weathering and is product when concentric folia are developed. Then biological weathering, there is the movement of mixing of materials, simple breaking of particles, then production of carbon dioxide by animal respiration or organic decay, changing in the moisture content of the soil, Bacteria, fungi, lichens, and moss are responsible for this. Then basic concept of geochemistry. Geochemistry is a science that deals with the chemical and composition and chemical changes reaction in the solid earth and its various component. Lithosphere, rock, mineral, hydrosphere, and ocean, river, lake, and atmosphere. It also includes the study of chemical species in the natural environment and the effect of human activities upon them. Major oxides. Major oxides are those whose abundance exceeds 1% of the total mass of the element present in the earth. Even elements are described as major elements because they form over 99 weight% of the most igneous rock. These major elements are SiO2, Al2O3, TiO2, Fe2O3, MgO, CaO, MnO, K2O, Na2O, and P2O5. Abundance of the element in the earth crust. Oxygen is 46.6% by weight, silicon is 27.7%, aluminum 8.1, iron 5, calcium 3.6, sodium 2.8, potassium 2.6, magnesium 2.1, all other 1.5%. Trace element. Trace element are defined as those elements present at less than or 0.1% or 1000 ppm, and their concentration are expressed in parts per million, that is ppm, or rarely in parts per billion, that is ppb. The exact definition depends on the field of science. In analytical chemistry, a trace element is the one whose average concentration is less than 100 parts per million or ppm. In biochemistry, a trace element is a dietary element that is needed in very minute quantities in the proper growth, development, physiology of the organism. Magnesium is a trace metal. In geochemistry, a trace element is the one whose concentration is less than 1000 ppm, that is about 0.1% of the rock composition. The term is used mainly in igneous petrology. Element zirconium may be the trace element in all other minerals, but in zircon and ZrSiO for mineral, it is a major oxide. Then the rare earth element. The rare earth elements are the most of the useful of all trace elements, and rare earth element studies have important application in igneous, sedimentary, and metamorphic petrology. The rare earth element comprises the series of metals with atomic number 57 to 71. It is from lanthanum to lutetium. In addition, the element yttrium, which is an ionic radius similar to that of a rare earth element, hafnium, is also sometimes also included. Typically, the low atomic number member of the series are termed as light rare earth element. Those with higher atomic number are termed as heavy rare earth elements. Then geochemical classification of elements. He classified the elements into four broad categories. Goldsmith was the first to point out the importance of these primary geochemical differences. He classified into four categories, that is atomophile, lithophile, chalcophile, and siderophile. Atomophile, sorry. Atomophile elements are volatile. Lithophiles, sidophiles, and chalcophiles refer to the tendency of the elements to participation into silicate, metal, or sulfide liquid, respectively. Lithophile elements are those showing an affinity for silicate phases and are concentrated in silica portions of the earth. Chalcophiles elements have an affinity for a sulfide liquid phase. They are also depleted into the silicate earth and may be concentrated in the core. Siderophile elements have an affinity for metallic liquid phase. Then you have high field strength element and low large ion lithophile elements, transition elements, noble metals. Then mobility of the trace elements. Geochemical behavior of trace elements is quite different from major elements. Absolute and relative abundance of trace elements such as zirconium, yttrium, niobium, gallium, and scandium are stable during the geological processes such as alteration, metamorphism, hydrothermalism, and weathering. The behavior of immobile elements is sometimes related to those of the major elements. Immobile elements, especially high field strength elements, are convenient for classification and altered rocks. The factors affecting the environmental mobility are chemistry, geology, hydrology, microbiology, gas transport, weather, and climate. Mineral is a natural occurring inorganic solid crystalline substance have specific chemical composition. Dana's classification of minerals include native element, silicate, oxide, sulfide, sulfates, halide, carbonate, and phosphate. The structural classification of silicate includes neosilicate, sorosilicate, cyclosilicate, ionosilicates, polysilicates, and tectosilicates. The common rock, common silicate minerals are grouped as olivine groups, garnet group, pyroxene groups, feldspar group, and silica group. Among all the minerals, plagioscale feldspar is the most abundant mineral in the earth crust. Rocks can be defined as the aggregate of minerals. There are igneous, sedimentary, and metamorphic rock. So these are the discussion that we finished the first part or first block today. Then the block 2 will be deal with the climatology, and the block 2 will be dealing with the climatology and the meteorology that we'll be discussing tomorrow. Okay, thank you, friends.
Thank you, sir. Thank you.
Thank you, sir.
So you have anything to share?
Sir, from these 4 units, which type of questions come?
Questions?
Yes, sir. From these 4 units, which type of questions comes?
I don't know. For the first time I'm teaching this course, you have to look at the last year's question paper, and there are some questions given in this PDF also. In this, while discussing, I didn't discuss those questions. There are questions with answers given here. They are also important. And also, you check the last year question paper, you will see are the questions coming in there. Maybe at the end of this 4 days, we can discuss few questions if time permits.
Okay, sir.
So I will try to get the last year questions, then I will share with you.
Thank you, sir.
Okay, thank you. Good night. See you tomorrow, sometime at 6 o'clock.
Thank you, sir.